Different slides. What are we doing today? We're doing this one. Hello, hello. We have one person here with us today. Do you mind sharing who you are? Great. So to the viewer there, I'm hoping you're doing well. Hope your studying is okay, and hope chemistry is your last exam. Thank you for joining, guys. All right, 9 p.m. Let's get a start on. Hi, everybody. I'm Layman. I've been doing these stream. This is my 4th stream. I'm very happy getting exposed to this sort of platform. Thank you for joining. So types of questions I'm going to go through today are enthalpy of neutralization related, and I'm going to sneak in at the end. Hopefully I get time to do an enthalpy of combustion. So your mod 7 fuels, all of that good stuff. Hopefully I can squeeze on in at the end of the lesson, but just want to quickly run through that. This particular dot point, conduct a practical investigation to measure the enthalpy of neutralization, has occurred quite significantly, not in 2019, but large amount in 2020, 2021, 2022 had 4 marks, so it's averaging about 5 at the moment. So if you do get this, hopefully you'll be able to answer it through revising and through doing these questions here with me here. All right, so guys, if you haven't already, feel free to download this version of these questions in the description below. Feel free to follow along, or if you're watching this at a later time, and this will be available as well as the answers. Okay, so let's get started with this. So first of all, what's a neutralization reaction? So a neutralization reaction involves a acid, base, and acid and base, and that gives you your salt and water. Now you got your other ones, which are your acid, metal carbonate, which gives you a salt, CO2, and water. Now this one is primarily what we're going to be focusing on today. This also does produce, this is also counted as a neutralization reaction. And as a general basis, acid and base reactions, neutralization reactions are exothermic, okay? So I wanted to throw this question out here first as a way to show you the different types of reaction. Hopefully you remember a bit of mod 3, which was about the reaction types. So first of all, we have this first reaction. First one isn't really a reaction, it's a change of state. So it's a physical change. This one's just melting. So melting draws in the energy. It's not exothermic, so not A. Second, electrolysis. Electrolysis is breaking water into your hydrogen and your oxygen, which requires energy essentially to break those covalent bonds there. You've got photosynthesis, which I'm sure you guys are aware now needs the UV light as an energy source intake. So also endothermic. So the last one we've got here is nitric acid with calcium hydroxide. So this is our lovely acid and base reaction, which is exothermic. Okay, so delta H less than 0. Right? Just abbreviation, you can do delta H equals less than 0 just to make it exothermic. So that's exothermic. And then delta H greater than 0 is your endothermic, right? So hopefully those abbreviations can help you save writing exothermic or endothermic, but whatever you guys like to choose. Okay, now this one related. So hopefully it's asked, you know, safety is always a big thing in not just chemistry, but anywhere really. So this one's saying the MSDS for a concentrated solution of glycolic acid states that it is corrosive to the eyes, skin, and respiratory system, and that is harmful if a concentrated solution of it is ingested or inhaled. Outline one safety precaution other than the lab coat or safety glasses that should be taken when handling this compound. Now, sorry, I didn't mention before, but there's always a reference here to where the question came from. So these are past exam paper questions. If you have access to those papers, feel free to look at those. You know, there's answers for those as well, but these are my take on it. So given the hint already, no lab coat. Lab coat is for skin protection. Safety glasses are for eye protection. So what is the next harmful thing that's in the way? The respiratory system. So if it can potentially cause harm to your respiratory systems, then don't breathe it in. How do you not breathe it in? You have a fume hood or fume cupboard, and or you can choose to have this in a well ventilated area. So you're working in either a well ventilated area or in a fume hood / fume cupboard. Okay, just to get those sort of out of the way, now we can jump into the calculation questions. So question 32, this one's from Norman Hurst 2019 trials, 32A. The diagram shows a coffee cup calorimeter used by a student to measure the enthalpy of neutralization of a acid-base reaction. 120 mils of a 0.5 mole per liter sodium hydroxide was added to 60 mils of 0.5 mole sulfuric acid. Both solutions were at a temperature of 24.2. After mixing, the final temperature was 26.3. Calculate the enthalpy change per mole of water. Now, this is very important. Now, just want to quickly note the mole of water. Now, the enthalpy change is always going to be based on the mole of water. So when we have our acid and base reaction, let's write up this one actually. So NaOH aqueous plus sulfuric acid H2SO4 gives us the salt here is Na2SO4 plus water. Now let's balance this up first. Okay, now the reason we use the convention is to use the mole of water generated. Okay, it's neutralizations are based on the mole of water generated. Okay, so we need to calculate the mole at the end and then to find our enthalpy. Okay, now how do we find that? So this is on the data sheet. So where is it on the data sheet? Lovely. It should be the there's 3 rows, should be in the middle row, far left should say this equation. So Q equals to MC delta T. Now what is each of these? Now for the neutralization reaction enthalpy calculations, the M is the mass of your solution, Okay, your C is the specific heat capacity of your solution, and your delta T is your temperature, difference in temperature. Okay, now what is the mass of solution? So we added 2 solutions. So we added a solution of 120 mils and a solution of 60 mils. Okay, so the total mass of that is 180 grams. Now we have to make an assumption here. So I'll put that underneath, in a bracket, assuming the density So the reason why we use density is we want to convert moles to grams. So we use this term, which is density, assuming the density of the solution is the density of water. Okay, that makes life so much easier. We also need another assumption later, okay, which is this one, the specific heat of capacity. Now this is also on your data sheet. This is the 4.18. All right, so we want to use that one because we're not given the specific heat of capacity for this solution, okay? In a subsequent question, we might get that, but when we're not given that, we have to make our assumptions, okay? So that's just 4.18 joules per gram per Kelvin times, so let's make that assumption as well. So also specific heat of capacity equals to waters. All right, back to this equation. Delta T is our temperature change. So what's that? So that's final temperature is 26.3. The initial temperature was 24.2. So that's 26.3 minus 24.2. Now, this can be in Kelvin, can be in degrees Celsius. For the purposes of the units provided on the data sheet, we want this to be Kelvin. Now, this doesn't matter because this is just the change at temperature. If I do Kelvin, it's still going to be the same. It's going to be the same as degrees Celsius. Okay, so what does that equal? So 180 times 4.18 times 26.2 minus, 26.3 minus 24.2. That equals 1,580.04. Now the units, after we've cancelled out everything, the grams, the Kelvin, we're left with just the joules. Okay, so 1,580.04 joules. Now, the next bit, quite fun. We need to calculate the moles. Why do we need to calculate the moles? Because we want to write this down first. The enthalpy is given by delta H equals to negative Q on N. Now, Q is what we just calculated. We need to find the we need to find the moles of water. How do we find that? So we need to look back at our neutralization reaction, right? So we need to first find the limiting reagent. The limiting reagent will determine how many moles of water we create. So let's try to find the moles of our NaOH first. How do we find that? C times V, right? This is V, this is C, V, C, all right? C times V, that's 0.5 moles per liter times 0.12 liters. What is that? Now, I'm very big on units, guys. For my students who are watching this, welcome. For the students who are not watching this, good luck. I'm very big on units. They know I'm very big on units. So make sure you write out all your units. Why? When you come to something confusing like your Q equals to MCAT, you're going to miss your units. Okay, if you write them out, you cancel them as you go, you'll make sure you won't forget them. Okay, so our moles of NaOH is 0.06, moles of our sulfuric acid is 0.5 times 0.06 liters. So let's write in our units. That equals 0.03 moles. Now I'm looking at these numbers and I'm looking at the molar ratios, and I can see that there's actually they're both limiting. Okay, so how do I prove that, or how do I show that? We can do our lovely molar ratio conversion. Okay, so based on the molar ratio or the stoichiometric ratios, we have 2 to 1. Now, what are our moles? We've got 0.06 to 0.03. So this is in the molar ratio of 2 to 1. So therefore no limiting. Oh, sorry, they're both limiting, not no. They are both limiting reagents. So that means I can use either one to find me the moles of water. So what is that? We can say, therefore, moles of water equals to the moles of, let's just, for the sake of it, oops, sorry, we didn't balance this. This should be a 2 there. For the purposes of that, we can say that's the same moles as our NaOH. Say 1 to 1 molar ratio. And then we can say that's equal to 0.06 moles. Okay, we're nearly there. Delta H, because the negative Q on N equals to negative. The Q value that we calculated earlier was 1580.04 joules over moles, which is 0.06. Now, we usually give our delta H, our enthalpy value, in terms of kilojoules, so we need to convert this into kilojoules. So that is just 1.58004 kilojoules. What does Q actually represent? Sam, welcome. Hello, how are you, my friend? Q means the heat energy released, okay? The heat for this particular calorimeter, okay? Just how much heat energy. So we end up with the unit of joules, which is a measure of energy. So how much energy is being received by that particular vessel, okay? I noticed there's a bit of lag with the comments. So Sam, if that doesn't make sense, please let me know and I'll explain that a little bit in a little bit more detail, okay? So what does that equal? 1.58004 divided by 0.06, 26 point, oh, let's go back up a little bit. 26.334 moles. Okay. 0.6. Yep. So, oops, sorry, not moles. Kilojoules per mole. Now we want to round that to how many significant figures? We want to round that to lowest is 3 significant figures. So we want to do 3 sig figs, which is 26.3 kilojoules per mole, 3 sig figs. Okay, so always end with your units and always round your number to the lowest number of significant figures, 2 being your lowest one if you don't have 2 as your lowest one. Okay. Thank you, Sam. Thank you for thumbs up. So, yep, that's it. Anyone have any questions, feel free to leave a comment. Let's go on to question 36, HSC 2020, the question, yep, from 2020. Okay, 100 mils of 2 molar HCl was initially at temperature 22.5 degrees. The mass of this solution was 103 grams. 10 grams of solid NaOH was added to this acid. The specific heat capacity of the resulting solution was 3.99 joules per gram per Kelvin. Okay, great. We've got a specific heat of capacity of the solution specifically. Assuming no energy loss to the environment, calculate the maximum temperature reached by the solution. Okay. Use the following information for your calculations. Why does it have to be in kilojoules, Mia? Great question. So it's just a standard way of representing enthalpy. It's just the typical units that we use. It's very similar to like, for our system, we use kilograms, we like to use meters of representing weight or mass and length respectively. Now, it might beg the question of whether you'll get the answer wrong if you're giving it in joules per mole. Personally, if it's the same, I will be fine with it, I think. But on a HSC scale, I think it's better to standardize everything in terms of writing the units based on what we typically see. So do know it. I think there's no reason to risk and play with fire a little bit. So report it in kilojoules per mole is my recommendation, Mia. Okay. Going back to the question. So what's this question asking? You know, what do we need to calculate? Okay, so what I can see this is happening is you've got neutralization reaction, but instead of your solution adding into your solution, you got a solid adding into your acid solution. So what happens first? I think they've given a very big hint, which is it first goes into ionization. So ionization of your solid to give you your aqueous ions. And then these aqueous ions then react with your HCl. Okay, so slightly different. Okay, so what do we do first? So we want to first work out the heat released from the ionization. We can see as exothermic, which is what we expect when we dissolve NaOH. How do we do that? We can get the energy from that. So we know we need to find the maximum temperature. So we need to eventually get back to this equation. How do we do that? So we need some sort of heat, okay? What Sam was saying, we need that Q. What is that Q? We need a Q from this reaction and we need a Q from this reaction, okay? So let's try to find the Q from the first reaction. I'm just going to denote this as NaO, Q of NaO, and then this second one as Q of neutralization. Neutral. Okay, neutralization. Yes, so how do I find that? So we're given the mass of NaOH, so we can do moles, and then the moles can cancel this one out. So let's do that first. So the moles is 10 over the molar mass of NaOH, which is 22.99. Now, hopefully you've done enough problems to remember or to memorize what Na is. So if not, that's okay. The data sheet is still there for you to have a look. So this answer is 0.22001250 ... moles. Then we can do delta H equals to negative Q on N. Now Q would therefore equal to, so if we switch that across, N, negative N delta H, which is 0.2500 ... times negative 44. Okay, what does that equal? Times 44.5, which is 111255568 ... kilojoules. Okay, we cancel the moles, we're left with kilojoules. So that's the Q of NaOH. Cool. Now we calculate the neutralization of the reaction now of our NaOH aqueous plus HCl aqueous. Now this is aqueous. Now that's been ionized. NaCl aqueous plus H2O. Okay. Stocks are very standardized acid and base reaction. Now, what do we do here? We want to then look at the Q released here, right? Or in this case, sorry, we want to look at the moles first. So, and then we can find our Q of neutralization. How do we find the Q? How do we find the moles? So the moles is again the moles of water. What is that? Is what we'd want to try to find. So we need to first find the limiting. What's the limiting? So we got the moles of NaOH already, perfect. So we want to find the moles of HCl. What's that? 100 mils, 0.1 liters times 2 moles per liter, which is 0.2 moles. Now, if we compare that in a 1-to-1 ratio, you can see that HCl is limiting because of the ratios being supposedly the same, should be 1-to-1. Okay, molar ratio, but we've got 0.25500 over 0.2, which is greater than 1. So that means HCl is limiting. So therefore we can say moles of water compared to moles of HCl is 1-to-1, which makes moles of water equal to 0.2 moles. So now we can calculate our Q of neutralization, which is negative mole delta H, which is negative 0.2 moles times our negative 56.1 kilojoules per mole, which is equal to 0.2 times 56.1, which is 11.22 kilojoules. Okay, so the total of them both contributes to the heat entering the system, aka affects the temperature increase. Okay, so the sum of both of them can be visualized as just a big Q. Okay, just a Q. So, and then we can start putting it into our equation, which is m cat. So mc delta t. Now, what is m in this case? M is just the combination of the two masses, or the two things that we've added into the system. So we've added 100 mils of HCl, but we've also added in, 100 mils of HCl, but that mass, is 103 grams, plus 10 grams of solid NaOH. So the total of those two is 113 grams. Now we don't need to assume any densities here because those are given in grams already. The C in this case is the specific heat of capacity, and now we're also given a different one to water. So again, we don't need to worry about the assumption statement there. And then the temp delta T is what we're trying to find. Okay, so if we can move everything except for the delta T to the other side, we should be able to find delta T. So delta T should equal to the sum of all the Q's, bit of maths there, over essentially MC. What's MC? M is 113, so the sum of those two in kilojoules, 11.1125568. Now the top is 22.3455628 ... kilojoules over the mass is 113 grams times the specific heat of capacity for that solution. So what does that equal? So first thing, we want to change the top to joules. So we need to times that to 1000. And then, so we need to answer times that 1000 over 113 times 3.99. So the delta T is equal to 49.560988 ... And now our delta T is equal to TF minus T initial. Now TF just means final minus initial. So we know our initial, which is 22.5 degrees Celsius. So in order to work out TF, it's just delta T plus TI, which is 22.5 plus 49.560988, which is equal to 72.0609 ... degrees Celsius. And now we want to round that off to 5333336 figs, so 72.1 degrees Celsius, 3 significant figures. Okay, so that is our max temperature. Cool. Does anyone have any questions on that? If you do, please leave a comment. I can go through this one again if you need me to, but be short on time. Hopefully we can finish this, let's keep on moving. Okay, this one's a bit of an interesting one. Okay, so as we looked at before, the the enthalpy is given by this, right? We're looking at the highest temperature change here. Okay, how do we get temperature in this particular equation? So we need to expand our Q. So expanding our Q gives us this. Now, if we want to isolate our delta T, what do we want to do? We want to move everything to the one side. We want to do N delta H over MC. Okay, I'm not going to worry about the negative because that usually cancels out with the delta H. Okay, I'm just treating like the delta H as a positive number. Now, how we look at this question should be the following. Okay, we want to try to make our lives as easy as possible by having some sort of ratio. Okay, because what this question is asking, the highest temperature change. So we want this number to be as big as possible. So we need to first find what's going to be constant. Okay, our delta H is going to be constant and our C is going to be constant, right? Because what's going to change is the number of moles of water that's going to be produced over the mass of the solution, okay, given by the volumes. Okay, so this will be a constant, let's say K, and then we can just find N over M. Whichever gives us the biggest ratio out of N over M will be the answer. Okay, so let's work out individually what the ratio N over M is. Now, you could go through all the steps and work out, oh, you know the delta H, but you're not given the delta H in this question. But this is, I believe, is the best approach to finding the answer. Okay, so let's work out the moles of HNO3, sorry, 0.05. So we first find the moles, find the limiting, find the moles of water, and then we can say that's the moles, and then we can add up the volumes to give us a mass. Okay, so that's equal to that moles. Yes, I can do that maths in my brain. Don't judge, please. Thank you. 0.1 times 0.4, 0.04 moles. So HNO3 is limiting. So that means the moles of H2O is 0.002. Now I've jumped steps obviously because I know this is 1-to-1 ratio. So I know that if this is smaller than that, that's this one's going to be limiting, okay? And that's equal to 1 equal molar as well. So that's our moles of water. We know our mass, which is 150 grams. So we can get our ratio N over M, which is 0.0025 over 150 grams. Okay, so what does that equal? 1.66 ... times 10 to the negative 5. Okay, now these numbers needs to be right, but they can be rough. Okay, they don't have to be. You don't have to. If you can work out the moles of water, you can work out the whatever. Just as long as you get this ratio right, and you can see which one's the biggest, and then you'll be laughing. Okay, so the moles of acetic acid, 0.2 times 0.05, which is 0. Okay, I'm going to use the calculator for this one. By any chance, if anybody has any mathematical concerns about their papers, don't be too confident about it. Feel free to use your calculator that you should be bringing into your into the exam. Okay, some people I know, they get a bit too confident and they end up typing in the wrong thing, or sorry, not typing the wrong thing, but they end up writing the wrong things, and just something that could have been avoided fairly easily. Okay, so did I get this right? I'm distracting myself, which is another bad thing. So again, 1-to-1 molar ratio. Moles of water should be 0.001, and our ratio can be now 0.001 over 300 grams. So we know this one's not it because A is still biggest. Now this one's a bit tricky because it's not 1-to-1 molar ratio. So let's work out the moles first. Moles of KOH equals to 0.4 times 0.05, 0.2. Okay. Again, this one is no limiting reagent because we got this. 1, 2, 2. Yeah, because this is diprotic, that is monoprotic, so that means you can use either one, and for the sake of the coefficients, this should be our moles of water. Moles of water. And then over the mass is 150 grams. Over 150 grams, which is, oh, I think we have another winner here. And then D, the moles of HCl equals to 0.2 times 0.05, which is 0.01 moles of our BaH2, 0.025 times 0.1, 0.0025 moles. Now our reaction is 2 to 1. Two to 1, and we've got 0.1 over 0.025. That's clearly bigger. The top's clearly bigger than 2 times that of BA bracket OH2. So BaOH is our limiting. So our moles of water here in this case is equal to 0.0025 moles. And then we can say our ratio N on M is equal to 0.0025 moles over the mass, which is 150 grams. So I'm not going to calculate that, but that looks to be less than this number. Okay, so our answer is C. Okay, let's keep moving. Half an hour. We've got 1 and 2 questions to go. Okay, perfect. I can slow down a little bit then. Okay, question 26 from 2022. Student conducted an experiment to determine the delta H of reaction between sodium hydroxide and hydrochloric acid. The data from one student are shown in the table below. Great. Yep, okay, so that means these are densities. Sorry, these are masses. No need to use density. We got initial temperatures. If we're mixing it, it should be an average temperature, which is 21.1, just the middle of these two. And then we got TF as well, which is the final temperature. Okay, perfect. Assume that all solutions have the same specific heat capacity as water. Okay, perfect. It's stated our assumption for us, so we don't need to mention that. So calculate the heat energy released in this experiment. So this experiment has that. So we're looking at heat energy. Heat energy is this Q, MC delta T, which is mass. Mass is the combined mass of these guys. Yes, combined masses of those guys in grams times the specific heat capacity of water times delta T, which is our final temperature, minus our initial temperature, which is 21.1 Kelvin, sorry. So we should be left with some joules value. Let's type that in. 102 plus 1007 bracket times 4.18 times 24.4 minus 21.1. 4 times 21.1. Yep. 2796.0438. Now, to give this in kilojoules, that would be 2.796048 ... kilojoules. And we want to round this one to how many sig figs? 1, 2. Have we used those numbers yet? No, not really. 1, 2, 3. 3 sig figs. So 2.80 kilojoules. 3 sig figs. Okay. Does that make sense so far? Yep. Following along. Yep. A second student, using the same procedure, obtained 2.6 times 10 to the 3. Okay, different. For the heat energy released in the experiment. Use this value to determine the enthalpy of neutralization, delta H, in kilojoules per mole for the reaction shown. Perfect. Our stock standard neutralization reaction. How do we do this? So the Q that the second student obtained was 2.6 times 10 to the 3 kilojoules. Now to work out delta H, we do our negative Q on N. What is N? N is the moles of water. How do we find the moles of water? We can find the moles of our NaOH, which is 0.05 times 0.1 liters, moles per liter, which is 0.005 moles. That happens to also be the same for hydrochloric acid, which is that. That means the moles of water is equal to N of NaOH, which is 0.05. Now we can just sub that in to our delta H, which is negative 2.6 times 10 to the 3 joules over 0.005 moles, which is equal to 520 kilojoules. Now I've already converted that to kilojoules because we like to report things in kilojoules, right? And now we want to round that off to 2 sig figs. Okay, that happens to be 2 sig figs already. So we can just end off the answer saying 2 sig fig. Cool. Cool. No questions, perfect. Let's move on to our bonus question that is not part of this dot point, but I'd like to go through quickly as well. We're going really good on time, so not stressed about that. Okay, now we've got our campfire. Okay, I ripped this diagram off another question, which is not a campfire, but imagine this to be a campfire. Student uses methylated spirits, which is mostly ethanol, a source of energy to boil the drinking water. Now, okay, you don't drink water in a beaker, but just imagine that's a metal cup being held on by a tripod. So write a balanced equation for the reaction of methylated spirits with oxygen. Great, so we have our ethanol, which let's say liquid, plus O2, gas. Combustion reaction gives you two main products, CO2, gas, and H2O, liquid. Now you get CO and C in incomplete combustion. Now I've talked about this more in my stream on day 2, so feel free to go on to there to look at that. Balancing, first off, balance the really difficult ones first. So balance your ethanol, 2, balance your water, hydrogens, which has 6 on the left, and then you want 6 on the right, and then you balance, go back, you balance the oxygen, okay? You've got one oxygen on the left already here, so the thing is you want to see how many you've got on your right hand side. So you've got 4 plus 3, which is 7, 7 minus 1 is 6, so 6 divided by 2 is 3. Camping stove that uses methylated spirits as its fuel heats a kettle containing 950 mils of water at 12 degrees, okay? So this is our T initial. Our water is our mass. Now, just one thing I want to quickly mention is this. Okay, use two equations to solve for enthalpy, right? Sorry for my ugly writing. This mass, a lot of people confuse this mass as the mass of ethanol used, okay? But that's not the mass of ethanol used, that's the mass of water, okay? This equation, you can think of it belongs to this little chamber. And then this equation belongs to this. How much fuel is being burnt, okay? This enthalpy is always a value of the fuel. So you use the moles, so you use the mass to find the moles of the fuel. Okay, only 40% of the energy provided by the combustion reaction is used to heat the water. Okay, so that means 40% of the heat energy, only 40% of the heat released is converted to heating the water. Okay, so we'll make note of that later. And then the final thing is, what's the mass of the methylated spirits that needs to heat the water up to boiling? Okay, so the boiling means TF, final temperature is 100 degrees Celsius. How do we start this question? Very good. Whenever you're dealing with this, always start with our MCAT. Now the mass is 950 mils, which is 950 grams, times enthalpy, times the specific heat of capacity, which is 4.18 joules per gram per Kelvin, times delta T, which is 100 minus 12 degrees. Say that in Kelvin. So we put that into the calculator. What do we get? We get 349,448 joules. Okay, so that's the heat energy that is used to boil the water. Okay, but before that, before we move on to our next equation, number 2 here, is we need to account for the 40% of energy that's contributed to this. So what this is saying is 40% of the total energy, let's say X, is equal to 349,448 joules. So how do we find the total energy that's being released by the burner? Okay, so we just move the 40%. The 40% is just 0.4. Move that over. What do you get? You get 873,620 joules. So this is your total energy. Okay, now we're going to use that to solve our delta H. Oh, sorry, to rearrange our delta H to find our N. Okay, the N of our ethanol is equal to, now we shift that over, put this one down, negative Q on delta H, which is negative 873,620. Now, I noticed that this one doesn't have a negative, but usually has there, so just add it in there. You know, exothermic means release, means away from you, so means losing heat. Okay, so that's that. Let's write in our units so that we don't forget. Now we need to convert the top to kilojoules. So we convert that to kilojoules, and then we divide that by 1364, which gives us 0.64048 ... moles of ethanol. Last step, mass of ethanol equals to moles times molar mass, which is 0.64048 ... moles times our molar mass of ethanol, which is 12.01 times 2 plus 16 plus 6 times 1008. Okay, what does that equal? 12.01 times 2 plus 16 plus 6 times 1.008, which is 29.5058 okay, and then that is equal to 29, sorry, not 29, that's equal to 30 grams to 6 weeks. Okay, so that's all the questions I've planned for. I realized I ran over time yesterday and I didn't even finish, so thought I'd end this one a little earlier. These questions, they don't get any different. It's all about interpreting the questions and finding the right numbers to use, where to use them. For these questions specifically, I would say the most important thing is for any enthalpy question, the key of these is to identify that your Q equals to MCAT is applicable to this vessel, and your delta H equals to Q over N is equal to this little section. Okay, in your neutralization, it's slightly different. They're all happening in the one place. Okay, so apart from that, units are very important. Okay, make sure you write everything out. Don't skip the working out. It's the working out that's gonna screw you up if you don't write it. You know, you go back and you check it, something's missing. You're gonna spend more time thinking about what you've written there when you could have just looked at something you've written there already. Okay, so tomorrow's going to be last session about, what's tomorrow? Tomorrow's going to be on equilibrium constants. So I know I want to also mention some equilibrium, sorry, I want to also mention the other constants, which are the Ka, the Ksp. So tomorrow will mainly be on equilibrium constants, but I'll touch on Ka, Ksp as well. So if you guys have any questions on that you want me to specifically answer, leave it in the comments today, and I'll work on that tonight and hopefully get something out for you guys tomorrow for our last stream together. Okay, thanks so much for staying with me for the live stream today. Get some good rest, and I will